Today, we want to continue thinking about what integration represents. And the format that we've established is that we integrate over some set and expression. And what we're doing is we're going to evaluate the expression at all the points in the set and then add up the results. Now, this kind of language is super fishy because I said evaluate the expression at all the points in the set. But the expression is changing continuously and the set has an uncountable infinity of points. So it's really weird what we're asking to do. We're asking to add up, but there's no terms that we can write here. If we have all the real numbers between 0 and 1, there's no next real number. So I can't make a list of real numbers. So it's really weird in our traditional way of thinking about addition, where there's a term, then a plus, then a term, then a plus, then a term, then a plus, and so on. What does it mean when we can't just list all of the terms? That's what's going on with integration. That's the difference between things changing discretely and things changing continuously. But the idea is still the same. We evaluate the expression at all the points in the set, whatever that means, and then add up the results. Now, the types of expressions and sets that we've seen, we can evaluate a function of one variable over an interval. We can evaluate a function of two variables over some region. We can evaluate a function of three variables over some solid, and presumably this could keep going. We can evaluate a function of four variables over some four-dimensional solid. We're just developing an expression that we're going to evaluate at a bunch of points. The integral part is telling us what points to plug into the expression. In the case of an integral, all we have is intervals. They're very boring. We only have one variable to work with. We need a set of one-dimensional things to plug in. It's just going to be an interval. When we get to regions, that's where things become interesting because the region can have lots of different shapes. And also we can describe the region in rectangular or polar coordinates. So our region has multiple types of coordinates. So we could do rectangular or polar. In the case of a solid, we're just listing a bunch of points that we're going to plug into the expression. And we have multiple kinds of coordinates to describe this solid. We have rectangular coordinates, where all three are distance, or all three of them are length. We have cylindrical coordinates, which is polar coordinates plus height. One of the coordinates is an angle. Or we can make two of the coordinates into angles and get spherical coordinates. In each of these cases, we'll have different pieces that we include in the DV to turn those changes in angle to changes in length. But the core idea is that we're just evaluating an expression at a bunch of points. So yesterday, we looked at variations in that expression. And we took a problem that was just a rectangle with a constant density, and we started including more variable factors. The one that we were using yesterday, out of convenience, was mass is equal to density times area. And the area broke down into length times width. In calculus, there is only one area, it's length times width. So the mass was the density times the length times the width. And we just started making one or more of those three factors variable. We also looked at the problem where we have a density, where the density doesn't change with the x or just with the y, but the density changes at any point, density changes as a function of two variables, x and y, changes in x's and changes in y's. So we couldn't draw a horizontal or a vertical line where the density was constant, because the density was only constant at some small point. And so in that situation, the dA had a dx and a dy. That's our area. Area is a length times a width. And in that case, the length and the width were delta variables. And we're just integrating the density over the region. Any questions? So this is the concept behind integration, what we're trying to do. Evaluate the expression at all the points in the set, and then add the result. What this can represent is our primary thing. Our primary use for this is that we're representing a product in which one of the factors is continuously variable. The f of x is continuously variable. We treat that as the length, and the dx is the width, which is shrinking down to 0. F of x could be the rate, which is continuously variable, and we take dx as a small piece of time over which we assume that the rate is constant. With a region, we pick with f of x, y, dA, we pick a point x, y, evaluate the function, and use that for a small piece of area, dx times dy. Integration is multiplication, but one of the factors is variable. So to come up with applications of integration, we just need to come up with applications of multiplication and then decide what it looks like to make one of those factors variable. Integration is multiplication, but one of the factors is variable. Specifically continuously variable, because if it's just regular variable, it just changes values. Then we can just use multiplication and addition. But since our factors are variable, we don't just get to use multiplication the whole time. So we're going to have to switch to addition. We have to drop down one level. So integration is addition. And that shows up in our description of integration. Evaluate the expression at all the points and then add the results. So integration is addition. Is everybody okay? So applications of integration are all our applications of multiplication where we can make one of the factors variable. What we're going to do next is increase the kinds of multiplication that we use. So multiplication isn't the only multiplication that we have. Multiplication of scalars, multiplication of real numbers. Since I just called real numbers scalars, you can probably guess where this is headed. We're going to start including multiplication. That's vector multiplication. So we have lots of kinds of multiplication. There's scalar multiplication. And we also have vector multiplication. There were two kinds of vector multiplication. There's a dot product and the cross product. So we're going to have to figure out how to set up integration where our multiplication isn't just scalar multiplication. Our multiplication might represent vector multiplication. And vector multiplication has two kinds of products, the dot product and the cross product. So we're going to have to work out the mechanics of what is it going to mean to integrate where we have vector multiplication. What if that vector multiplication is a dot product? What if that vector multiplication is a cross product? Questions? Comments? Beautiful. So for this, we're going to need to define vector value functions. So next up, we need to start talking about vector calculus. We're going to start talking about vector field. These are functions with outputs that are vectors. So a vector field will take each point in the space and assign a vector to it. So instead of just saying assigning a number to each point, we're going to assign a vector to each point. So here's an example of a vector field. The input is just any point in R2, and the output is going to be a vector. So notice that this particular vector, if we have a vector function, if we evaluate it at 0, 0, the origin, we end up with the 0 vector. Notice that when we plug in 0, 0, we're plugging in an entire point, x and a y coordinate. And notice that the 0 we get is not just 0 the scalar, it's the 0 vector. Because this function gives you vectors as outputs. We look at the point 1, 0. Then the output vector is j. If we look at the point 1, 1, and the output vector is 2i plus j. We'll look at the point 0, 1. I also get the 0 vector. So at each point, we are going to be plotting a vector. So the graphs are going to be very different than the graphs that we're used to. Normally we plug in a point and we get a height, just one scalar, one value above that point, the height above the point. But now at each point x, y, I'm not drawing just one point, we're drawing an entire vector. So the graph will look like a bunch of vectors. So at the point 0, 0, we just have the 0 vector. At the point 1, 0, at the point 1, 0, we have the vector j. So 0i plus 1j. At the point 1, 1, we draw the vector 2i plus 1j. And at the point 0, 1, I would again just draw the vector 0. At every point, we're drawing a vector. If we look at the point, say, 2, 1, so x is 2 and y is 0, I would once again have 0i, but then 2 squared is 4j. So I'd have a vector. And here's where we get into some messy bits. I'd have to draw a very long vector, and they would all cross over. Because at each point in the xy plane, I'm drawing an arrow. They'll all have different lengths. And moreover, this 2i plus j, I just realized I was double scale, but I put that at normal scale. So that's only half of what it should look like. And we can see that 4j is going to be way too big. There, I only drew it 3. So we're not going to usually be able to draw the entire vector. So what we'll do is we'll just indicate a direction, and we'll use length to indicate magnitude, but we'll scale things down. I'd want to note that the vector is at 2, 0 is much longer than the vector at 1, 0. But it's going to be hard to represent if I just draw a bunch of vectors. Question? So these are vector fields are functions where the output is a vector. Let's see how this could show up if we use a dot product in an integral. So now that my function is a vector field, I have different kinds of multiplication available. One kind of multiplication is to multiply a vector by another vector with the dot product, and the result will be a scalar. Right now, what is this going to be? Let's set it up like we did before. The vector field f dot some change in the points. Also, what kind of stuff are we going to be plugging into this vector field? So how do we complete this expression, and what kind of set? Because one thing we'll note is that whatever variable drops in here, this needs to be a vector, because the dot product is a vector times another vector. What kind of set can we evaluate this expression? Because the basic rules of integration are always the same. We're going to evaluate this dot product at all the points in the set and add up the results. Then think, what does that mean? That's the mechanic behind it. With this in mind, our applications of these integrals with dot products will be the same applications that we have for the dot product. Just like if we want applications of integration with scalar functions, we look for applications of multiplication. Here, we're going to look for applications of the dot product, and those will now be applications of integration. Question? Let's see the big picture, not the whole big picture, just the rough big picture. The integral says evaluate the expression at all these points, add up the results. We're doing the same thing here, but now we have a dot product instead of just a regular product, a scalar product. I shouldn't call it regular, as if it's like better or more normal. It's just the one that we're most familiar with. So now we have the dot product instead of just a scalar product. Just a scalar product. Now I'm insulting the scalar products. A dot product instead of a scalar product. Now everybody's okay. And then we evaluate that expression at all these points in the set. So what kind of points are we going to have in the set? Well, if my vector field is a function of x and y, then my points in the set are going, for f of x, y, our points in the set is going to be some collection of points in R2. So for our set is just a bunch of points in R2. Here's the first kind of set that we're going to deal with. Now we're thinking about the big picture of what integrals represents. We're going to talk about line integral. A line integral is a bit of a deceptive name. It's really more of a curve integral. The set over which we will be integrating will be a curve. The set over which we integrate is a curve. We can do this in R2 or we can do this in R3. We can have parameter, we can describe a curve in R2 or R3. Our small piece, the dx or the dA or the dv, what's standing in for the small bit over which we assume that the function is constant is going to be, has to be a vector because we're making a dot product, and it's going to be, we're going to call it dr for reasons, not r for reasons. I just realized those now. Because the same kind of thinking in building this line integral, the same kind of thinking in building any integral goes into building this line integral. We're going to assume that the function, the vector field is constant for some small change in points on the curve C. So C is some curve running through a vector field. Once we define a curve, either running through R2 like I have one here, or running through R3 like I have one here, if you imagine going up and down some. At each point along this curve, we can evaluate the vector field. This is how integration works. I've defined a set that we're plugging in. We evaluate the vector field at each of those points to find out what that vector is. So at each of these points along C, there's going to be a vector from the vector field. Evaluate the vector field at each point along C. It's fishy to say each point. C is a continuous curve. There is no next point. But that's just running in the background of how we think in calculus. Now we need to make a dot product, F dot dr. So I need to make a dot product. All these vectors F, I gotta find a dot product with some other vector. The dr is going to be a small piece of the curve in vector form. We're just going to take a little piece, the tangent of a vector tangent to the curve. Because what we do is we say that the function, the vector field F is constant for some small change in C. Small changes in C will be described with tangents. So dr is tangent to the curve C. So at each point, we're evaluating this function, this vector field. And we're also we're going to use that value for some small change in the curve. So the dr is that small change in the curve, tangent to the vector field. So at each point along the curve, I've got what the vector, where the vector field is pointing, and I've got where the curve is pointed, what's tangent to the curve. So at each of those points, I calculate that dot product, and I add up all the values, all those dot products along C. And since we're finding a dot product and adding up those values, this is going to be a scalar. Right now, there's a lot of unfamiliar shit going on. Vector fields, that's new. Describing this curve with a bunch of vectors. I don't just have a curve running around. I've got a curve and there are little arrows telling us which direction the curve C is going. So clearly we're going from left to right on this curve. And then the dr is all these tangents, but it still fits into the way that we think about integration. Integration is multiplication, but one of the factors is continuously variable. In this case, the vector field is continuously variable. The direction that the curve is pointed is continuously variable. So we assume things are constant for some small change in the vector in the curve, modeled with the tangent to the curve. Then we calculate that dot product, move on to the next point, even though there is no next point. Evaluate the vector field, find tangent, the vector tangent of the curve, find that dot product, and add that to the sum. Question? Now, what's missing here is a lot of the machinery. This is the thinking behind what the line integral is going to represent. We need to develop a lot of machinery so we can make this, actually make calculations. But as we're going through, we're going to have to pick some application of the dot product to be our first application of line integrals. How's everybody okay? First day of vector calculus. A lot of times we just take calculus and add stuff to it. So I know all of you are math majors because I don't actually, maybe none of you are math majors. I think I've had a math major this year, so I don't think any of you can be math majors. I'm only allowed one per year. I'm just kidding. You can all be math majors if you want. Any takers? No? I don't really do a good job of selling it and just explain what math is like. And you're like, oh, we're going to be engineers. We don't care how things work. We just care that they work. You know what I mean? And then your friends are like, well, why is everything in your house a workaround? You're like, well, because I'm an engineer. I just need to make shit work. I'm just kidding. I'm not making fun of the engineers. Okay, I am, but they make fun of mathematicians too, so. Fine. What are we talking about? Oh, yes. So we're going to need some application of the dot product so that we can use that as our basic application for line integrals. I think the one that I want to use, since we don't really have areas equal to length times width, I think the one that we're going to use is work is equal to force times distance. As we start with it's a nice concept. Work is equal to force times distance. If something is heavy, and it's going to take a lot of work to move it. If something is lighter, but we move it for longer, that would take the same amount of work. The reason that dot product is going to play into it is if we're trying to go one direction, because the curve is telling us to go this direction, but we're in wind or water, and the wind is the vector field pushing us, trying to push us this way, then our work is going to be dependent upon how angled those vectors are to each other. The wind pushing on us, the direction we're trying to go. The wind pushing on us, the direction we're trying to go over the entire path. But we wanted to start off thinking about how integration works and upgrading it to deal with vector value functions. What's it going to look like in general when we have vector value functions in our integrals? Any questions? Comments? Snide remarks? Math majors? No one's ever a math major in math. It's really weird. Actually, it's not that weird. Took me a long time to decide to become a math major. And I was the first student math major that I met. Oh, I changed my major. Really weird. All right. That's going to do it for today. I will see y'all on tomorrow when we'll talk more about line integrals.